Welcome everybody. Thank you for coming. I know it's rough to be here on a holiday. But remember, when the days before Thanksgiving roll around and Thanksgiving comes, we will be done, correct? Couple of announcements. In one of the previous classes, someone asked me a question about the test on the 11th and whether it was going to be giving on that date. And the answer is no, because there is no test on the 11th. Our first test is scheduled in the syllabus for September 18th, which is a week from this coming Friday. You guys had me scared. I'm going, how am I going to cover all this material in 3 days? And I went on. You can always check the class schedule by going to Canvas. I do it myself. If you go to Canvas and click on the link for this course, I essentially have that schedule there, and it shows which days are A's and B's and the approximate subjects we're covering and also the exam dates. And I check that myself just to make sure everything is okay. I also want to remind you now that we've changed how we are doing the quizzes. The quizzes will only be given on Wednesdays. For those of you who will be here live, that's those of you who are watching this video right now, you will be doing the quiz live here in class. For those of you out here today watching, you'll be doing it online on Canvas, okay? Right now, I have a dummy quiz posted on Canvas. You can take it multiple times. If you've never taken a quiz on Canvas, you can take it multiple times just to see how it works and get used to it. I will remind you that the quiz will be online, will be only open from 10 to 10:30. You don't have infinite time to do it. I should actually open it from 10 to 10:15, but I know people are late and stuff happens. Cover your nose, please. Cover that nose up. If you're in the middle of the quiz at 10:29 and 10:30 comes by, it will lock you out and take the answers that you've had up to that time. So get in there and do it early. It's only 4 questions. It'll be very easy, just like the one that we had here. Also, it will tell you your score. All right, it will tell you your score. I haven't decided yet whether I will let you know the correct answer or not. I think I'm not going to do that because it's probably better not. We haven't seemed to have trouble with those quizzes, so I may or may not tell you the correct answer. But yeah, I will tell you the score. Okay, and I also dropped the lowest quiz. So if you miss a quiz for whatever reason, don't cry too hard. I will automatically drop the lowest one just because that kind of stuff happens, you know. Our first exam, which will be in about a week, almost 2 weeks, but a week and 5 days or so, will be on chapters 1, 2, and 3. Chapter 1, the main thing in chapter 1 is the 7 ideas. Know what are and are not the 7 ideas. They'll also be on chapter 2, which we have pretty much finished, which is Copernican astronomy, and there is a review sheet out for Copernican astronomy. That is an approximate review sheet. Every single thing is not necessarily on that review sheet. I was going to have review sessions and then decided against it because of the COVID-19 thing, and also the fact that everything is available for review by watching the videos. So the videos will all remain up there through the end of the semester. You'll notice that under the description of the videos, I have the takeaways or the ideas that I covered during that video to help you locate something. If you couldn't remember Ptolemy's theory, then you can look under the playlist, look at the description, and you'll see one of them that says Ptolemy's theory, review of Ptolemy's theory, or something like that. The test will be multiple choice, which is very much like the quizzes we've been having, okay? Part of it will be multiple choice, and part of it will be matching. The matching are kind of like multiple choice with 10 different answers. So a matching is essentially what you're going to have is their multiple choice, but with 15 different answers. So let's see. First, had a geocentric model that could not explain retrograde motion. There is an example of a matching. And then there'll be 15 names numbered: Aristotle, Ptolemy, Galileo. How many other people can I name? La la la. Yeah, roll your head around there. It feels really great. Okay. Yes. Yeah. Find a good masseuse. So there'll be something like there'll be a few multiple choice with a large number of answers. Okay. There'll be some of those. Okay. I'm not sure how I'm going to work those yet, but they will be there. Okay. And there are going to be 4 exams, and also we're going to have some extra credit. Dr. Spates has got this month's star show out. So I will be sending out an email with a link to that. And the way it will work is that you watch that video. It's like a 25-minute video. You watch the video and write a minimum 1-page double-spaced report on it, and you will get the equivalent of 5% on a midterm exam. That actually can add up. Doing an extra credit, doing 4 or 5 extra credits can raise your score in this class by half a letter grade, so they can be substantial. Okay, so be aware of that. So I'll be sending that out this week as we get going here. Will I send it out today? No, because doggone it, it's a holiday. And I don't want to sit out at least under the sun for a while, but it'll be out soon. Okay. Okay. Where the heck did we leave off? I think I was talking, about Aristotle's theories of motion. And I talked about his idea of earth, of air, of fire, and water. And in those substances, we have related to that a special type of motion. We saw that Aristotle had several categories of motion. Again, Aristotle is 300 to 400 BC. This is a long time ago, almost 2,500 years ago. Yes, sir.
You wrote water twice.
Say again now?
You wrote water twice.
Oh, earth or air, huh? Uh-huh. No, you're supposed to tell me what I'm supposed to write. You're supposed to say you wrote water instead of air. Okay. Very good. Usually you say earth, water. I forget the order they usually listed in. But Aristotle had several categories of motion. One was heavenly motion, which we have discussed ad nauseum. We started our discovery or our description of the heavens with Aristotle's theories of heavenly motion. And then he talked about sublunar motion, motion in the sublunar world. That's what we're covering now. There are several categories down there. One of those categories was alteration. And what you really need to know about alteration, as far as I'm concerned, because it's not truly motion, it's not a change in position with time. It's sort of a change of something as time passes. That alteration is not a category of motion from Aristotle that we think of as motion. But I list it for completeness. The 2 categories of motion in the sublunar world, though, one of the major ones was natural motion. And this we saw is vertical motion. Natural means, what does the object do when you don't mess with it? When you don't touch it, blow on it? There's no, there's different things, there's nothing influencing it. What's it going to do? Well, he said it's going to either rise or fall. That's vertical. And he says that earth and water fall because they seek imperfection. So he ties this in, sort of the battle between good and evil, yin yang and so forth. Fire and air naturally rise because they seek perfection. And if an object contains all of these, such as a cigar I discussed, we know that a cigar falls. A cigar falls. Well, it has all of these in it. Evidently, the water and earth in a cigar outweigh the fire and air, take more precedence, there's more of them, and therefore that's why a cigar falls. Okay? On the other hand, if you have wood, wood is made mostly of earth and water too. When you burn wood, fire, and air doesn't mean just this air. Air means gas. Smoke is kind of like air, okay? You burn a piece of wood, fire and air come off, water and ash are left, and these are the ones that seek imperfection, these are the ones that seek perfection. Then he talks about vertical motion, which is called violent motion. Violent or projectile motion. And this is horizontal. You have to throw the object in order to get it going sideways. If you drop something, I don't care if you truly drop it, it will never drift sideways. There has to be something unnatural or something influencing it that causes it to drift sideways. Throwing a baseball. The throwing action is the violent part of it. Once it is caught, the catching of it is the violent part of it. If smoke drifts up, that's natural motion, but if it then drifts sideways, that's the violent part of it. That's caused by a wind or something forcing it to go sideways. That's violent, okay? So you had natural motion, violent motion, alteration, and then you had heavenly motion. Now there are problems here. In particular, Aristotle had great difficulty describing the violent motion. Natural motion, that's caused by the battle between good and evil, seeking perfection, seeking imperfection. That was his explanation for why something would go up and down. But the problem that he had with violent motion, he could see that when you threw something, you were influencing it. He could understand that's what got it going sideways. And when it was caught, catching it influences it. It's not natural, it's violent. That he could understand. The problem is, what happens while it is in the air? In fact, the motion that we're seeing now is actually a combination of two motions. The natural motion, I throw this up, it returns because it's seeking imperfection, and so it comes back down. If you were to take like a balloon and push the balloon down, it might go down for a bit and then go back up. So he understands this part of it. If I throw this upwards towards the other hand, while it's moving sideways, it is still seeking imperfection. So if it's going up, it still comes down. So there's this motion, the up and down natural motion, and then there's this sideways or violent motion. The problem is, once it leaves my hand, what keeps it going sideways? He understands the starting and stopping. He does not understand this, what keeps it going in between. He really believed that there had to be something affecting it in between. And his description of what kept things moving in violent motion is called antiperistasis. Antiperistasis. Stasis means not moving. Anti, not moving. And I think you're going to see that this is pretty hokey. And I think Aristotle didn't like it either, but it's the best he could do. You do your best. You can't always figure it out. Hollywood always shows everybody figuring the whole thing out. No. Half the time you only get half of it right. Here's what he said. If an object is moving to the right, say an arrow, whatever, he says that the air in front of it is pushed aside and rushes around the back and pushes on the back. Okay? That the air in the front rushes around to the back and pushes on the back. You write that down, whatever you want to say it. The air in front moves around to the back and pushes it and keeps it moving.
The air in the front moves to the back and starts
Pushing on the back to keep it going. That's exactly right. He didn't like this. He could find problems with this. He could find that there are some situations, how does this, I don't know. You know, like, for instance, this runs into trouble, sort of, what if you have an object like this? Okay, how, how does the air push on the back, but somehow, evidently it did, okay? Though it's harder to understand with something like an arrow point or something like that, but this is what he believed. Though he knew there were problems with it. All right? Now, a couple of very important conclusions that Aristotle made. After performing many experiments, that means actually doing something, okay? He didn't do the experiments in the sense we think of nowadays in a laboratory, but he would try things out, and what he concluded was that if you look at a moving object and you wait long enough, what ultimately happens to any moving object? Come on, somebody. Does it continue to move? No. Every time you have a moving object, it ultimately stops. This is one of the reasons they rejected in their heavenly studies that the earth was moving. Everything we observed stopped. So he makes the conclusion that, one, the ultimate state of an object is one of rest. So some conclusions of Aristotle. Oops, let's at least capitalize his name to honor the man. The ultimate state of an object is one of rest. All objects eventually stop. A state of rest. Everything stops. They never observed anything that continued to move forever. And this had an influence on his ideas of heavenly motion. The earth couldn't be turning on its axis, it couldn't be moving through the solar system, because that would require something to keep it going, and this was never ever observed. So, the ultimate state of an object is a state of rest. 2, he concluded that you could not have a vacuum. Now actually, before I get to that, let's look at something else. He also concluded, so let's just list some of these, A, B. He said, and this seems to make sense, heavier objects fall faster. This, again, seems very reasonable. If we take my textbook and we take a small piece of paper, I hope the camera will pick this up. So we've got a piece of paper and we have the textbook. We know that the book falls much faster than the paper. Definitely. Okay? Heavier objects fall faster. However, every object that is falling through something. If I take a rock and drop it in air, and then I take the same rock and I drop it in water on the beach, say from waist height, it falls much more slowly through the water. If I drop it through oil, it'll fall even more slowly through the oil. Or molasses, or something that the Greeks might have had. They knew that the medium through which it fell affects the rate of fall. The medium is that which carries the objects. The medium affects the rate of fall. The medium is that through which the object falls. Air, water, molasses, whatever. This was easy enough to do. You could have a tank of water of some kind. I mean, the Greeks had pools or whatever. And you could drop an object from your waist and watch it slowly go down through the water. You could step out of the water, have it drop the same distance. It goes much faster in the air. And this led to a third important conclusion of his. He concluded that if you could somehow remove the air, if you could somehow take the air, I mean, they believed in air because all you got to do is see a house blown over in high winds, and the air is really there. Just because it's invisible doesn't mean it's there. That if you tried to somehow remove the air, then the object would fall faster. And if you removed more air, it would fall faster still, and more air, it would fall faster still. And therefore, he concluded, you cannot have a vacuum. You cannot have a vacuum. If you did, an object would fall infinitely fast. He says that the only thing that is limiting the fall of an object in the air is the presence of the air. And as you remove the air, it would fall faster and faster and faster. And if you sucked out all the air, it would be every place at once. It would be going infinitely fast. That can't possibly happen. So you cannot have a vacuum. Not possible. Now we know now, as we're going to see, that some or all of these may not be true. Nonetheless, they were supported by experiments that they had back then in 300 or 400 BC. So, are these correct? Well, as time passes, some of these come into question. There are some experiments you can do, such as B, which show there's a problem. Because if I take the book, the very same book we had before, and the very same piece of paper that we had before, and I put the paper on, let's put the paper under the book. Okay, what's going to happen now? Who can tell me? Don't make this hard. The book pushes the paper moves exactly in step with the book. So I can explain that. The paper falls faster in this case because the book is influencing it. Okay? But if I put it on the top and we repeat the experiment, what we find is the paper falls lockstep with the book. Not only does it go faster, it goes exactly with the book. Well, it's not glued or stuck to the book. It's not, you know, I didn't, if I tape it on the book, well, yeah, okay. But if I just set it there, it still goes lockstep with the book. That doesn't make sense. The paper is still in air. It's in the same medium. The book is definitely a lot heavier, yet the book is not falling faster or the piece of paper isn't falling lighter. There are some problems here with this, okay? There are some problems there. And then later on, the church ruled out C. The church said, God can do anything. God wants to make a vacuum. God can make a vacuum. You can't essentially say that nothing is impossible. And so, over another 1,000 years or so, some of these teachings of Aristotle start to run into trouble. Okay? Some things start to run into trouble. Another thing is that the idea that when you throw something sideways, this idea of antiperistasis, which nobody ever really liked, that starts to fall out. Instead, people start to believe that perhaps when you throw the object, something is given to it, which we now call momentum, but back then, you know, which they called it impulse, which tends to keep it moving. So as time passes, several of these start to fall apart. And of course, a lot of the other teachings of Aristotle, such as on the heavens, they start to falter too. Now, before we get to the truth or find out what's really going on, we have to learn how to visualize motion. It's nice to describe motion mathematically, and we will, but we also need to be able to visualize it, to categorize motion based on graphs of the motion. So what I want to look at now is how do we graph motion, and how do we recognize certain types of motion. It's the ability to graph an object moving and put that on a piece of paper, and then to be able to look at the graph and figure out some of the basic characteristics of the motion, such as how fast is it going. In fact, if you go and say, well, how do you describe motion, we're going to get into terms like velocity and acceleration. But velocity and acceleration can be explained in terms of graphs of motion, and that's the way that I prefer to do it. The most basic graph of motion is a graph of position versus time. The symbol T is used for time, and for hundreds of years, who knows who first chose it? X denotes position. And in one of the great Indiana Jones movies, they talk about they're at this church or library in Venice or something, and they find the markings of the entrance to the ancient catacombs, and he climbs up the stairs, and there's this huge X on the floor, and he goes, X marks the spot. Jeez, okay? And of course, on treasure maps, the treasure is always indicated with an X where the treasure lies. It goes back, I don't know, hundreds of years. Someone just did it once and it stuck. Okay? Someone just did it once and it stuck. Now here's how we do it. What we do is we're going to consider for the moment one-dimensional motion. When you try to do 2 and 3 dimensions, you get into trouble with a graph. But you can do an excellent job of representing linear motion in one direction easily on a graph. And typically what we do is on the graph, we represent position vertically. Position vertically. And this might be, say, in meters. A meter is slightly longer than a yard, it's not the same. And then we draw a timeline, and where the timeline intersects the position axis, that is our origin, the point that we call 0. In other words, that is the 0 mile marker. Well, for us, I'm going to put the 0 mile marker right at camera center. This is 0. Positions to the right are going to be considered positive, and they're represented up here. Positions to the left here, these are going to be represented down here. If I step over a certain distance and I just stand here and I graph this, at each point in time I make a dot on the graph upwards from the 0 point, I'm going to get something like this. And if I connect those with the line, I get that. If I stand over here in the negative region, about the same distance, and make a dot at each point in time when I'm here, it's going to look like that. Like that. These are the data points. See? Now, these two lines have something in common. They're not the same line, but they do have something in common. What is it? Well, first of all, are they straight or are they curved? They're straight. They're straight. But they have something in common. What is it? When you draw a straight line, you talk about the slope of the line and the intercept of the line. Do these have the same slope? What is their slope? 0. The slope is the steepness of the line. If the If they slope upwards, that's a positive slope. If they slope downwards, that's a negative slope. These have zero slope. Zero slope. And the condition here is I am not moving. On the other hand, if I start over here and I go like this, nice and smoothly, I'm going from a negative position, crossing the origin and going to a positive position. And you see, that is again a straight line. Okay? What would it be like if I start here, now watch, and halfway I double my velocity halfway. Then what that will look like is that. I'll have a graph that looks like that. And clearly, if I do move, we see that I get depending on how I move, but if I move uniformly, let's do this, like that, then I'm going to get something like this. And if I were to start here and then go backwards, I would be doing something like this. But all of these lines have something in common. What is it? What do all of these lines, let me take the data points out. As long as I change my position equal amounts in equal times, I can get something like that, or I can get something like that, I can get something like that, but they are all straight lines. If the line isn't horizontal, I am changing my position. If the line is horizontal, I am not changing my position. What we see is, for this one, the velocity is 0. Whoops. Well, the velocity is 0 for that one. Here, you're going forward. And for this one, you're going backwards. What we see is that the slope of the line tells us the information about whether I'm going forwards, backwards, or not moving forwards or backwards at all. I could be going backwards very fast, like this. In other words, I can actually say that the velocity of the object is the slope of the line. On a position versus time graph, the slope of a velocity v versus time t, we actually do this. It is defined to be the velocity. And from basic geometry of graphs, the slope of the line is equal to its rise over its run. And so it is the change in x over the change in the time and we use the Greek delta symbol to represent D, or difference. The delta means difference. If you're in a fraternity or sorority with a delta in its name, delta means difference to the scientific folks. It is the change in the velocity over the change in the time. Well, both of these. But graphically, it is the slope of a position versus time graph. Here, the slope is negative, and it's quite steep. Negative slope means negative velocity. Negative velocity means you're going backwards. Here, you're going backwards really fast. Here, you're going backwards maybe half as fast. Here, you're going forwards. Here, you're not going forward or back. There, your velocity is equal to 0. You see, by looking at a graph of position versus time, we can learn a lot about what the object is doing. But the key thing here is that the change in position with the change in time is the velocity. Okay? This is what we mean. Look at how your speedometer. Now, a speedometer is a little bit different. A speedometer doesn't tell you whether, you can actually put a speedometer in a car, it won't tell you whether you're going forwards or backwards. Okay? Cars typically have speedometers. Speed is how fast you're going and is always positive. We say mathematically that speed is the absolute value of the velocity. The speed of an object is not the same. The speed is defined as the absolute value of the velocity. So over here, if you say, technically, what velocity is the greatest? The answer would be this one, because this is positive, negative, and negative. A positive velocity is greater than a negative velocity. But if I say, where is it going fastest? I say, where is the slope steepest, regardless of whether it's going up or going down? That's right here, without a doubt. Without a doubt, okay? So here's what we're going to do next. We're going to pursue this further, and we're going to look at situations where I just don't move always the same way. I'm not just going to go like this. Okay? What's it going to look like, for instance, if I speed up? So I go like this. Or what if I speed up and stop, and then go backwards for a while, and then stop, and then go forwards for a while? That's going to look strange indeed. It sure as hell isn't going to be a straight line. No. I'm going forward, I slow down, I go backwards, I slow down, I go forwards and do something like that. Heck, now it's not a straight line. Well, still, looking at that, one of the questions we'll ask is, let me label some points. Call this A, B, C, D, E, let's suppose it goes like that, F, and G. Where was I stopped for at least a little bit? What letters was I stopped, if only for a moment? B, D, and F. Any place with a graph leveled out for no matter how short of a time. B, D, and F, I'm at rest. Where am I going forwards? A, E. What am I doing here? At C, I'm going backwards. At G, I'm going backwards. At E, I'm going forwards, and so on and so forth. Let us stop there. Have a great holiday, and we'll see you back here soon. Bye-bye.